Greetings everyone, Free here. Welcome to the Demo Hub. In today's tutorial, we're going to talk about a fascinating concept. You might have heard but not really sure what a vector database is, what a vector data type is, what a vector search is, how is it related to the whole concept of databases or Gen AI or LLMs. If you are hearing about this for the first time, this tutorial is for you. Before we jump into the tutorial, all the scripts we walk through will be available here on the Demo Hub tutorials. This site curates all the tutorials and the scripts. Click on Snowflake Embeddings and Vector Search. There are detailed tutorials along with all the scripts for you to follow. There are also links. Tutorials.DemoHub.dev will be the site for the scripts if you want to follow along. That said, let's walk through some examples. What is a vector database, or what is a vector search, or what even is a vector? And why is that important more so than everything else we've done in the space of databases and database programming? To start, we're going to go ahead and create a database. Very simple, nothing to write home about. This would be called Embeddings database. Now, the Embeddings database is empty. Next, insert some objects into the embeddings database, and we're using this just for illustrative purposes. So what are we inserting into the embeddings database? We're going to insert some everyday objects. These are objects you might be familiar with. We're going to insert a chair, a table, a book, flower bed, galaxy hunt. We'll see why we are inserting these specific objects into this table called everyday objects within the database. Run this. Takes a few seconds. Now we have a table. Verify that. Refresh the schema. A database called embeddings. A table called everyday objects. Browse that. We have those everyday objects within that table. All good. Next, and this is where the concept of vector databases and vector search starts differentiating from what we see in the Gen AI landscape versus what used to exist in databases before. You create a relational table, you insert objects, in this case, a key, a pair, a string, or varchar. Typically, in the world of databases, you can come in and write a query to the effect of select star from everyday objects we're working with, where object name like P, the predicate, which is very common in SQL. We should return everything within the database, in this case, that starts with uppercase P and everything else. Straightforward. Run this. SQL is really good at running queries like this, where you have a string, doing string matching, and you search across the database to return based on a particular pattern of a string. It returns a pen and it returns a phone for us. Let's say we want to do a search, and I'm going to introduce a new term here called semantic search. Let's say we want to search for everything within the database where the name is like writing. Okay? If I search for this, where the name is like writing, nothing is returned, but let's just go back here and do the search across the entire table. Just by looking at this, because we have a very small data set here, so I can peruse this. There is a pen, there is a book, maybe a table, even you write on a table, even a computer, you can write a paper on a computer. If my goal is to search across my database, not for matching specific strings, but trying to search for the semantics. So semantics essentially is meaning of a particular word or a particular query. The way databases have been in the past is you will struggle to get this query to return a result for you. Because I'm searching for writing, it should be smart enough to know maybe pen and writing are similar enough from a semantic perspective. So we should return the pen. But in this case, we get nothing. No amount of string matching will allow me to return pen in this query, because pen and writing are related, or writing and computer are related. This is a challenge which existed in the past in databases before this whole world of Gen AI. Let's try another query real quick. Search for something where object name is like animal. Do a search for this. Again, no result. But this is not what we want. Do a search on the entire table. You see, there is beaver. Beaver is an animal. I would hope that it should be smart enough to return beaver. The fact that we cannot return beaver is a problem. Unless you know there was beaver in that table, then you put in the text, but you don't always know that. In the past, we've always done string matching, and the goal for showing this is that there are limitations to interacting with data if all we had as a tool was basically matching strings. We miss the meaning, we miss the semantics behind the fact that an animal or a beaver is an animal, or writing goes with a pen, or writing goes with a computer. So this is a challenge that we've always had in the past. This is where the whole idea of generative AI and embeddings come into play. So what are embeddings? Embeddings is a way of a large language model being able to take any input string you give or text, maps that into a higher dimensional vector space. So it gives you a vector representation, which it encodes meaning into the text in a higher dimensional space. I'm trying to keep this a little bit simpler just so you understand the vocabulary. Think about it as you have any text you want, send it through an embeddings function, which is a large language model function. That function takes the text, it gives us a vector. A vector is basically just a set of numbers that you can plot. If you remember from algebra, you have an x coordinate, your y coordinate. If it gives you a vector of 6 and 6, you go 6 to the x, 6 to the y, and you plot that on a two-dimensional vector space. If it gives you 5 and 7, you go 5 to the x and 7y, and you plot that. This is a simple example of a two-dimensional vector space. But in reality, the vectors you get from an embeddings in the LLMs will be way more than this. You're going to be getting n-dimensional vector spaces, which we cannot even visualize, but the computers are really good at working with that. This is the concept of an embeddings, and here is a simple illustration of this. Now that we understand embeddings, let's go back into the database and see how we can take advantage of embeddings and do more sophisticated searches with the data you have in your environment. Snowflake provides an embeddings algorithm. If you've heard of Snowflake Attic Embed, this is so powerful because you can use these embeddings to embed the data within your Snowflake platform, and it allows you to do more semantic search on that. Looking back at the previous table we had, these are the objects that are in there. There's object ID, object name. Now call a function snowflake.cortex.embed, specify the embedding algorithm, in this case, Attic Embed, give it the object name. We want to embed car, for example, or house, for example, or food, for example, or any column you have. You can run this embedding against any column in your database. The net result of this is it takes the object, gives us a vector representation of that object in an array format. But this is an embedding. Now, this is a higher dimensional embeddings because you cannot plot this if you go back in a two-dimensional vector space the way you would do from algebra in high school, because there are many more dimensions in here. Each one of these commas is a dimension. But the computer is really good at working with things like this. Even though these numbers look random, they are not random. They encode meaning. And what you would see is the embeddings for pen might be similar to the embeddings for writing or for table, because maybe people tend to write on a table. Or the embeddings for table might be very similar to the embeddings for chair. Now you might ask, but Fro, how does it know to be similar? The similarity or the meaning is where the large language model comes into play, because the large language model is what is doing the embeddings, and you don't have to worry about that. Simply say Cortex embed, you give it your objects, it gives you a vector representation. If you have enough of those, kind of how, let me just talk back to this example. If we did embeddings of these objects and we plotted them on a two-dimensional vector space, objects that are similar will cluster. In this case, I can see some of these objects are similar. Then over here, these objects are close. These objects are far apart. If I'm doing a search, say, give me objects that are very similar to this object, I should expect this ones around to come back. Now imagine if this object was a pen. what I'm pointing at here, and I say, give me objects that are very close in distance to a pen, maybe a table, maybe a book, maybe a chair. You sit on a chair to write. Things that are similar would come back. This is what we call a vector search. Once you have a vector, you can then start doing search for what is close or similar to that vector. Visually, this is what it looks like. Now, if we switch back into the table, once we have our vectors, you would not be doing manually a vector search on your vector embeddings. But Snowflake does provide another powerful function which you can use to do the vector search against the data within your vector. Run this, it creates a table called Everyday Objects Embeddings. Refresh this. We have a table here called Everyday Object Embeddings. Verify. We have the corresponding embeddings. Now, just having the embeddings in itself is cool, but here is another cool function we're introducing, this vector cosine similarity. Cosine similarity is a way of doing a search across vectors to give you things that are similar to a particular vector within your vector space. The vectors we have is the embeddings vector, if you remember. So that was the column name. And we say Snowflake.Cortex embed to text. Essentially, I'm saying take this word tree, embed that tree. Once you have an embedding for it, line 5 is my embeddings. Line 6 is stored in DB. I'm doing a vector cosine similarity search and saying, give me things that are similar to the tree to what is stored in the DB, which is just looking at the column. This should give me things that are similar. Now take a look at what we get back. We get tree, door, flower, hunt. This is cool. You couldn't do something like this before if you were just doing string matching. It just would not work. This is something that couldn't be done in the past. Now, we are not searching on strings. We are searching on meaning. And the function is what is doing the search for us. So if I say, give me something similar to book, and I do a different search, it's not just looking for things that start with the name B. It's giving me table similar to book, giving me a key. Maybe a key is in the book, or a book is a key to success. House, maybe a book is in a house. Hunt, maybe it's a book about hunting. Once you've done your embeddings, you can now start doing similarity searches. So this is a vector similarity search on that vector in a powerful way. This is something that you couldn't do before. Super powerful. Do Galaxy as an example. It gives me Galaxy. Obviously, there's Galaxy on the table, so it matches that one-on-one. If the match is exactly the same, it tells you how similar it is. It's a one-to-one. Now, you can do a lot with this. For most people, your tables are not filled with books and phone and food and computer. You have more sophisticated data. You have your patient data. You have your customers' data. You have your inventory data, your supply chain data, your product catalog data within that. Now you're looking to search for which product do we have similar to another product. Or maybe a customer has surgery and you want to say, show me all my products that are used for surgery. If you have the right embeddings and you've trained the model or fine-tuned the right model based on your data, you can start doing things like this on your data set, whereas basic string matching will not do it for you. This is why this is so cool. Let's go ahead, take this and put it all together. So what I'm going to do next is create a table called documents chunk. And you might have heard about RAG, so retriever augmented generation type applications, where you have, say, PDFs, typically unstructured data documents that you might be working with. Create a table to host those documents. Insert sample data for illustration purposes. Verify what we have. Again, all of these scripts are available on the tutorial guide. So if you want to follow along, just follow from that. Let's say here I have a PDF. You extract the data from that PDF and you store them within Snowflake. There is some pre-processing happening. I'm assuming you've already done the pre-processing using something like DocAI or Python functions in Snowflake or Snowpark. You can take PDFs and read through those PDFs and store them in the Snowflake table. Here is the text from that PDF. Now that we've seen what is in the documents, let's go ahead and take advantage of embeddings again. Now that we've taken our text we've run through the embeddings. Guess what? We can start doing searches against that embeddings. So I can ask any questions to it, and the embedding should give me a result. So like before, we're doing a vector cosine similarity, which is a function provided by Snowflake Cortex. As always, you take the input from the user in natural language, sales growth in Q1. So assuming somewhere in here we're talking about sales growth in Q1, we take that, we embed. So now we have an embedding, which is already stored in the database. We have an embeddings here coming from the user. We can then compare and say, go search in my database, give me the chunk or the piece that is most similar to what the user has provided in their own embeddings. Go ahead and run this. We get sales growth in Q1. It returns this chunk. The report summarizes sales performance. All right, so this is what it returns. Now, this is not something to write home about. I don't think we've done anything too profound here. We're just basically showing the functions. Let me do a quick select statement up here just to show you. Take a look at this text. This report summarizes the sales performance for the first quarter of 2024. Just pay attention to that text. Let me query the original table. We're searching across all of these chunks and basically just returning the entire chunk. We haven't summarized it. We haven't done anything. So in here, it finds and returns for us this chunk. And that's why I asked you to pay attention to that text. This report summarizes the sales performance for the first quarter. So it's returned all of the entire chunk. If all you wanted was just to get a chunk back, what piece in your database answered the question, sure, you can take the chunk and use it for the most part. But the reality is most people who deal or build these applications, you might want to summarize this. So a better approach would be once you receive the entire chunk, maybe summarize that chunk for me. Maybe translate the chunk for me. Do something with it. Do some other functions to that chunk. That is what Gen AI and some of these LLMs are good at. The very first thing is let's run this piece of code, which we did before, is going to return for us a chunk. We send it out to this outer select. We can now use Cortex Summarize. This is a powerful function. If you haven't used this, we've done tutorials on this already. Snowflake, the Cortex Summarize, passing the chunk summarize is really good at it. It takes any text you want and it gives you a summary of that text. See the original chunk and the summary of it. Run all of this. The original question was, what was the original question? Sales growth in Q1. That's all we prompt. That's the only thing we've asked. And here we get the summary. The report details a 15% revenue increase for the company during first quarter of 2024 compared to the previous year. That's the response we get. And how are we getting that? It's a combination of a couple of key concepts we've touched on. Vectors, vector database or vector data type, where you take text, you create vectors, you store them in the vector data type, which Snowflake supports. And the way you do that is you do an embeddings functions, which we saw how to do embeddings. Once you have that is you come in and you do a similarity search by doing an embeddings on your input. You search, you get the closest text. Once you have the closest text, you can then apply things like summarize, translate, Q&A, and a lot of other functions that Snowflake Cortex provides. This is the building blocks of having very powerful Gen AI at your fingertips. Now, Attic is one embeddings model. There are other embeddings models you can use that Snowflake supports. I'll highly encourage you to check out the documentation, but here we're doing the demo, just we're using Snowflake Attic as an embeddings model. Now, we can take this in future demos and check on the channel. Again, we might have done a demo on this already and build this into a Streamlit app with a nice UI. So instead of a user coming in and prompting this in a SQL statement, you can have a Streamlit application that simply takes the prompt from the user, queries the database, looks at all the embeddings, figure out what the chunks are, summarizes that, translates it, and then you have a nice chatbot on top in 14 lines of code, or if you include the Streamlit piece of it, Streamlit in Snowflake, you might have maybe 15, 20, 30 lines of code, but it's still simple. It still democratizes access to all these powerful models. So hopefully this was helpful. This is a tutorial we've covered. Again, all the links are available here. There are some additional links below if you want to read more about Snowflake Cortex, an overview of that, what embeddings are, which we've touched. Hopefully you have a good orientation of embeddings, vector search, and how that becomes useful. As always, go in, try it out, apply it to your use case. It's so simple today to achieve some of these things that in the past used to be difficult to do. Coming from the trenches, where I just remember having to do things of fuzzy matching, fuzzy lookups just to rationalize customers, or figuring out what are my customers buying and being able to summarize that. GenAI gives you all the powers to do that now at your fingertips. Again, hopefully this was helpful. This has been Fru here with DemoHub. We create tutorials like this. We take the complex, we hopefully make it simple for you. If you do like this, do us a favor, share this with somebody that might get value out of it. Like it. I think YouTube always likes it when people like the videos. If there are topics you want us to cover, let me know in the comment section below. I'll see what I can do. As always, thank you for sticking to the end. I'll see you in the next demo.